Thank you. All right, good evening, everyone. So I will today touch upon a very interesting topic of a word that has kind of become a bit cliched in the whole LLM talkosphere, a word called hallucinations. But we've spent a number of years at this point working in this area. So today I'll hopefully walk you through the journey of how we've evolved detecting hallucinations and sort of similar errors in language model generations, and all the way to some of the more recent innovations that we've done in using SLMs to detect RAG hallucinations, and a lot of the benefits that we've seen in using an SLM over that is fine-tuned over using prompting-based techniques. So just a little bit about myself and the company. So I'm one of the founders of Galileo. We are basically into LLM evaluations and observability. And we started the company pretty much around the same time as Predibase. We kind of came out of the same lab at Stanford and then eventually grew from there. And a lot of both founders of both companies kind of spent pretty much of the last decade building machine learning platforms for Google and Uber. So I spent many years at Uber before, and I was leading multiple areas of their feature infrastructure, including one of the engineering leads of the first feature store that we had built many years ago, and eventually was heading up evaluations for all of Uber's machine learning. So a lot of lessons learned over the many years. We started the company in around January of 2021, so over 3.5 years ago at this point, and we were essentially started with the thesis that evaluation tooling for ML in general was kind of broken, and for language models in particular, it was much more of a black box. And so we started off building these algorithmic techniques that would automatically detect noise in your data as you would train your erstwhile BERT models, which was a very popular practice back in the day. This is a little screenshot from one of our older tools where you could literally auto-sniff the embeddings from a training job. We would color it green and red based on the data noise that we detected using a proprietary technique, and that would really help you hone in on specific areas of data that are bringing your model down. But today, I'll, of course, shift gears and talk about the new era, which is the LLM era, and just the general non-deterministic nature of these LLMs. I think a lot of us have spoken about the fact that these LLMs are essentially just token spewing machines. They're a token by token probability distribution, which somehow stitches together a sentence that makes sense to humans. This is a famous quote by Andrej Karpathy from back in the day that essentially everything an LLM says is a hallucination. But then there was this whole quote around whether these dream machines that are spewing out dreams, are they a feature or a bug? Essentially, this kind of points to two things. Number one is even the best models, they often go wrong, and wrong is very subjective. It could be right in depending on the task at hand, it could be right or it could be wrong. And also the fact that these kind of more subjective questions come because there's no quantified way of evaluating whether something's right or wrong. And these are sort of examples where it essentially just showed that even the most, this is of course old news from maybe 6 to 8 months ago at this point, but even the more modern models were essentially causing havoc for some of these bigger companies. So we entered into this era of non-deterministic software, because now we are starting to build software with a lot of these LLMs as little nodes in the mix. This is an interesting graph. So we've moved from 2023, which was the year of POCs and experimentation, to 2024. As far as considering the biggest problems or biggest challenges, inaccuracy in the model's generation, as well as intellectual property infringement, turned out to have the highest net increase in what practitioners thought as important. Whereas the long tail of other issues around privacy and fairness and explainability, they didn't have as much of a change in understanding or importance as we've kind of started to mature the toolscape and started to really take these LLMs seriously. So now, how are AI teams detecting or evaluating hallucinations in particular today? I'm going to talk a little bit about that. So just taking you back in time of, I guess at this point, early 2023, when the whole LLM landscape kind of changed and right in front of us, detecting errors in the generations kind of boiled down to three techniques. So the number one was n-gram matching. And hopefully I'm just speaking to the choir here. It seems like an advanced crowd, but we all know what n-gram matching is. It's essentially taking your tokens or pairs or like tuples essentially of tokens and then doing some kind of matching between two sets of sentences to assert similarity. Number two is a practice that eventually emerged as people started experimenting more with LLMs, which is Ask GPT. And LLMs as judges, self-checking techniques, etc., kind of fall under this umbrella. And the third is, of course, the caveman tooling, which is human evaluations. And you'd be surprised to know how common human eval is even today. So just going deeper into the three techniques here, n-gram, of course, there's standard methods which are used, the blue and rouge scores, which we already spoke about earlier. They're essentially comparing some semblance of token level matching. And you can improve that by using synonyms, etc. But these are all very old school NLP techniques to say that, oh, two generations are very similar. They do work in certain cases, at least erstwhile, these used to be the standard techniques to evaluate seek-to-seek or generative models. They tend to work in machine translation tasks, summarization, image captioning, but the limitations are obvious. We're in a new era where these models are kind of speaking like humans and not necessarily techniques which are matching words and sentences will give you a good sense of whether something's good or bad or right or wrong. So they're very limited in their methodology. They also require a ground truth. Now, ground truth is something that's not necessarily available, especially as the bar for starting to use these generative models has gone so low. People not always have these data sets and ground truths ready. So the reliance on ground truth is a very, very big impediment. Also, models are more creative and innovative in the way they speak, these larger models. So you can say the same thing in a completely different way, and you have a ground truth with completely different tokens, and you do some kind of matching, and you'll get a low score, and that's essentially a false positive. And of course, they're very granular in their approach. The second technique, interestingly, became pretty popular in 2023. There was a paper that was written in July from the University of Cambridge, which essentially introduced this idea that if you want to detect hallucinations, you should use a LLM which is smarter than the source LLM. So from there, there were a whole bunch of techniques which came out using things like self-check BERT, which will basically do multiple calls to another LLM and then sort of do a BERT score between the original generation and the subsequent generations. The notion being that a response is hallucinatory if the BERT scores are vastly different across the different calls. So very, very similar techniques started to emerge. Again, very similar applications. The shortcomings here are, of course, the fact that you're just asking another LLM to say whether something's hallucinatory or not. There's so many restrictions in that. It's black boxed. It's dependent on the memory and the training data of the hallucination LLM. And it is prohibitively expensive, especially at scale. And this is coming from first-hand experience as we've seen people start to move from experimentation to evaluations, even at throughputs of 10 million queries a day, which is not really very high. If you think about it at a second level, it's maybe 15 or 20 generations a second. The evals can cost you many millions of dollars in a year. And the general lack of explainability, because you're essentially querying a magic 8-ball, and asking it to answer. And the third one, I don't think I need to go too deep into this. Just the other day, I saw someone open an Excel sheet and there was a little column, is hallucination? And they were writing yes or no. So we realized this early on, and we sort of went down this journey of creating a new category of LLM evaluation metrics that, number one, needed to be accurate, because accuracy is pretty much everything. There's no point of serving anything for cheap or fast if you're serving garbage. The next is scalable. There's all different kinds of tasks these models are used for. But when I say scale, I mean the breadth and the coverage of the kind of data that can sort of be deemed hallucinatory or not. Third is cost effective. Of course, people have budgets, and like I said, when you start productionizing these systems, there's enough throughput that can lead to many millions of dollars in detecting hallucinations. And finally, low latency. Again, this is a consequence of starting to productionize things. One of our key learnings this year has been people essentially want guardrails and evaluation algorithms in the line of request. So as a user is you interacting with, say, an LLM-based chatbot, you essentially want to detect hallucinations in real time and maybe mitigate or redact issues that you detect. And the latency SLA for those are much, much lower. And just in today's erstwhile talks that we saw, you saw the generational latency for some of these LLM-based techniques. They're like 10, 15, 20 seconds, which is pretty insane. So with this in mind, we kind of went down creating two new techniques to detect hallucinations. And we wrote a lot of research about it. It's been published many, many times, and we've been doing years of work on this. So I'm going to touch upon both of them, more the latter one, which is based on the SLM. But first, I do want to introduce the first technique, which we called Galileo ChainPoll. Now, ChainPoll was the first technique which took the whole concept of using another LLM to determine hallucinations to the next level. And it really introduced this idea that you can't simply ask another LLM a simple question around whether something is wrong with this generation or whether something's hallucinatory, because that technique will never scale. That technique becomes very, very expensive once you start getting into the nuances and you start generating is hallucinations or not for every single generation. So there's many things that went into improving that. And there's two aspects to ChainPoll. The first is chain of thought prompting, or chaining, which basically said that you need to use the chain of thought technique to make essentially go step by step to detect reasoning mistakes in order to detect hallucinations with high efficacy. And the second was polling or ensembling. And this was an interesting realization which came from an early discovery we made with some of these modern LLMs, in that these LLMs are not great at sort of giving you scores between 0 and 1 or 0 and 10. What they are good at is binary classification. So you can give them a lot of thought and reasoning and context and make them say yes or no, and there was step function difference in accuracy in its ability to, say, generate a score between 0 and 1 on anything, any criteria, where, say, 0 is low and 1 is high, versus yes or no questions were like 20, 30% more accurate. So the thinking here was that you use a chain of thought to make sort of a step-by-step decision on hallucination detection. But then you don't do a single call, you have to do polling, which is you do multiple calls to it, and you kind of use majority voting or some kind of a polling mechanism, because each call would be a binary classification, and then you can take the n calls that you've made and kind of create a score that quantifies hallucinations. So here's how ChainPoll works. You have a user which makes a query to the LLM, and you get back your completion, and optionally, sometimes you get back your log props. Not all LLMs will give you these log props. So if you don't have log props present, what we do is we have an a magical way to generate log props at a token level. And that's a sort of a proprietary algorithm that we've built. And if you do have log props, we send the completion and the log props and the chain of thought prompt to our chain of thought module, which does the chain of thought inferencing and ensembling within it. Now, the number of judges is kind of the number of times you sort of make the call to the LLM. Within chain of thought, we've done a ton of optimizations to do basically all of this in one single call. So we use batch inferencing and various other techniques to essentially make sure that if n, which is the number of judges, is greater than, I don't know, 5 or 7, you still make just a single call. And all this is possible using batch inferencing. And then we get the output of this. This goes into a cleanup and optimization module, which is just general sort of software, feature engineering and software cleanup. And then we finally get a score between 0 and 1. We do categorize hallucinations into two. Number one is open-ended, open domain hallucinations, or just factual correctness. And the second is RAG hallucinations, which is essentially given a context and a generation, how much is the generation adhering to the context or sticking to the context. And this is important to know because as we move to the second technique, which is using an SLM, this is a key piece of knowledge to remember. So one quick thing I'd like to point out here, ChainPoll is not an LLM, right? It's essentially a framework which basically says that you need to take advantage of chain of thought as well as ensembling to detect hallucinations with high accuracy. And we've built this framework with all these boxes being plug and play. So one of the key benefits that we've seen is a framework like this just piggybacks on all the innovations that are being done today. For example, with one of our customers who uses ChainPoll in production, we replaced the default ChainPoll model which we used. They were in OpenAI shop, so they used GPT 3.5 and we replaced that with 4.0 mini. The costs dropped by like 60-70% immediately without sacrificing accuracy. So this is a snapshot from one of our papers. The general AURC score for ChainPoll was on like 11 or 12 data sets, which we collected into what we call RealHal. And it gave significantly better performance compared to some of the other Ask GPT or LLM as judge techniques. Now, some of the advantages were very high accuracy compared to other evaluation methods. Because chain of thought is essentially a method to make the LLM think step by step, we were able to curate an explanation for why something is hallucinatory or not, which has proven to be extremely advantageous for users of our platform. Because not only do they get like a score, but you really understand why something's hallucinatory or not, and then you offer that through an API and you can do a lot with that. The other thing was there was no optimizations made typically in standard Ask GPT methods that people would use. They would essentially construct a prompt and throw that to an LLM. There's a ton of optimizations we've done, like batch inferencing and a lot more, which essentially reduces the cost of these LLM calls, and you get a lot out of the box. And finally, the fact that it does add an LLM in the loop, it is costly. And the third is it is hard to customize for a use case. This is basically the whole prompt versus fine-tuning debate where you can only achieve a certain level of customization with prompting. And while ChainPoll offers you the ability to add feedback to make your metrics evolve with your data over time, there's only a certain amount of improvements that you can get simply because of context size limitations and the number of examples you can share with it. Which is why we moved to our second technique, which we call Luna. Now, Luna is an SLM, so it's a small language model, and it is a specialized model that is used to detect hallucinations in RAG use cases. So We started off with, you kind of went on the other side of the spectrum. We took a 400 million DBERTA model and we fine-tuned it on a lot of data that we've collected, because we've been in this business for almost 4 years at this point. We've been collecting hallucinations data for that long, and we've really used that data to train a Luna. And we've been able to create like a small model, which is essentially an entailment model or an NLI model. So the reason we used NLI was because we reduced the definition of what hallucination means in RAG use cases as you have a context and you have a generation, whether the generation is entailing the context or is it contradicting the context. So it's a standard paradigm in NLP, but it fits very well with the definition of hallucinations in RAG applications. So we collected that data. We were able to, of course, get all the benefits of a small model that can run efficiently on an L4 GPU, ultra low latency, very adaptable. I'll talk about the adaptability in some of the innovations that we did. Very generalized, as well as we allow the users of our platform to curate data sets from their production and fine-tune Luna, which achieves insane levels of accuracy compared to any kind of LLM as judge or any kind of prompting techniques. So 4 innovations that we did on Luna. These are interesting because we took such a small model, and how do you make a tiny model compete with these large giants and try to achieve the same level of accuracy was a pretty daunting task. For various reasons. These small models have insanely small context lengths. So to solve the context length issue, we used a novel windowing approach where you take your RAG context and generation and you kind of divide them into overlapping segments. And this is like just training data feature engineering. And subsequently, you train this auxiliary model on every possible pair of the context window and the response window. What this also gives us is sentence level hallucinations. And I'll show you a screenshot from the Galileo product, what it does. Because we are able to generate yes or no scores of hallucinations at a sentence level, we are able to literally tell you that if the model got a generation wrong, which part of the model, which part of the context did the model use in its reasoning and where it was wrong. The third was multitask training. Now, we saw hallucinations as one part of the sort of bigger problem in RAG quality. There's a lot that goes into RAG. Of course, there's multiple pieces. You have vector stores and you have these hyperparameters which allow you to tweak chunk size, and all that is to say that you want to monitor not just the quality of the generation, but you also want to see how much of the chunks were utilized in the generation to tune the number of tokens you're sending, because you're essentially, if you're querying an LLM, you're paying by the token. Beyond hallucinations, which is what we call context adherence, how much of the generation was adherent to the context, you also want to measure completeness, like how complete was the output. Maybe part of the model did not use part of the chunk where relevant information was present. So we trained this model to be a multi-headed, multitask model, which gives you, in one inference call, you get essentially 4 metrics, which give you sort of a holistic evaluation of your RAG system, not just whether the output is good or bad. And the third is, I was talking about data generation, and one of the secret sauces of Luna is really just the data that we've been able to curate and collect over many years at this point. But also, we've used synthetic data techniques to cover increase coverage of the standard sort of industry where RAG applications are used. But also, we've done some very interesting data augmentations to make such a small model understand nuances in language, which typically larger, like double-digit billion parameter models sort of have naturally. So in computer vision, you would do techniques like augmentation and image flipping or pixel flipping, etc., which are typically computer vision feature engineering methods. We applied them to language, and we saw some step function improvements in such a small model. So those were the 4 sort of key innovations we did. And then we did the same benchmarking of the Luna model. And it turned out to be 18% more accurate in detecting hallucinations, say if you just directly query a GPT 3.5 model. So this just really speaks to a few things. The power of smaller models, if you train it on the right data, if you train it the right way, if you really, like, in a very diligent manner, train it on the right tasks, you can get a lot more than if you just simply use a large LLM. The biggest bang for the buck was, of course, cost. I already mentioned, this is a comparison of Luna's cost with other eval techniques and eval algorithms which are out there. And you can see that because it's a local model, it's a cheap model, it's the only one which doesn't have an LLM in the mix. The costs are astronomically lower. And finally, there's the latency. And again, we already saw a slide where, I think it was a checker slide where they said that the latency is around 15 seconds for some of these generative models. This one, it's just 200 milliseconds. So it matters because, of course, the rate at which applications are being put into production almost mandate the need for low latency, low cost, and high accuracy. It's that challenging trifecta that you have to solve. And without that, it's very hard to scale evals for any application. And I'll show you a few fun screenshots of the product itself. So this is a little, like a Streamlit chatbot that someone made, one of our customers, and here you can see essentially this is Luna in action, but what it's happening is it is detecting a PII, which is one of the Luna models, and then it will automatically redact it. But you can see the speed at which it's able to do it. I know this might not be exactly giving you the objectives and latency numbers, but I have them from Grafana. They're very, very low. In the Galileo suite, Luna suite of metrics, we offer more than just hallucination metrics. There's RAG quality metrics, which allow you to measure chunk attribution, chunk utilization, how relevant were the context, and how complete was the output. There's safety metrics, which help you detect toxic content and bias and PII and prompt injections. But the whole platform is very customizable because there's custom use cases, custom data, and you can essentially fine-tune these models to adapt to your use case within the platform. This is one simple screenshot of a trace that you can evaluate using Galileo, but on the right-hand side is really the magic, where you automatically get context adherence is low, which is a sign of a hallucination, but then you kind of take it a step further where you can hover over it. We give you these explanations, highlight areas which are hallucinatory, and even at the chunk level, we can highlight areas where the LLM was reasoning, the tokens that it used to reason about in its answer. So there's a level of explainability which you'll not find in traditional techniques or any kind of open source method. All right, thank you.
Thank you very much, Atin. Just in the interest of time, I think we'll keep it open for one question and then try and go towards our final talk, but yes.
Thank you. My name is Spark. I'm a solution architect. Thank you for the sharing. You mentioned many anti-hallucination methods. Really, thank you. But one slide worries me that is when you talk about Luna, since Luna is a hallucination based on RAG, so the definition of the hallucination is LLM is talking something that is not based on your context. However, when you do the evaluation, I found that even the Luna is the best accuracy achieved 78. There's still 20% of things hallucinate. So that worries me that in this case, how do you facing this kind of reality? Is this kind of result ready to on production? Thank you.
No, that's a great question. So what we've seen is a 78% baseline accuracy is pretty state of the art. What that says is agnostic to any use case. If you just use Luna out of the box, like about 8 out of 10 times hallucinations will be detected, but there's always the last mile or last 2 miles where we can fine tune Luna. So what we've seen is with one of our customers, I can't name them, but they went from about 82% baseline accuracy of RAG hallucinations to 98% by fine-tuning on about 150 samples of production data. So it's really the last mile is, you can't get better last mile accuracy than outside of fine-tuning.
You can't get away from fine tuning either. Awesome. Thank you very much.
Thank you so much.
Thank you very much, Atin.